So yeah, hello everyone. First of all, thank you for the kind introduction and also the invitation. I'm very excited to be here to talk about our recent work on the stability analysis that we did on the ODD complete Friedmann equations and stringy gravity with my advisors here, Professor Savaş Arapoğlu and IB Kezar. Today, as again said, I will talk about the stability analysis that we did first on the flat ODD complete Friedmann equations, and then we compared it with the phenomenological model of chameleon cosmology. And afterwards, we looked at the curved configuration of the ODD complete stringy gravity to see the dependence on the curvature of this model and see whether it prefers the flat universe or closed or open universe configurations, and see how its dynamics tells us about the curvature. So I will first start with the brief outline of my talk. At first, I will give some motivations that why we studied the alternative theories of gravity models, and then continue on with the stringy gravity, the phenomenological stringy gravity motivation that we use the compared with the chameleon models, and why we choose to work on the ODD symmetric system, and what's its advantage on the other string theoretical cosmological models. And then I will just tell the why we choose the method of dynamical system analysis as a method of our preference. And then I will just briefly introduce you to the linear stability analysis by just like giving some very toy example, just like give you the idea of the algorithm of the linear stability analysis, so that we can understand why we choose to work on this method. And then finally, I will present you that the models, the configurations that we worked on, such as the flat ODD symmetric universe, and why the comparison with the chameleon cosmological model. And then after these comparisons, I will give a quick summary on the results that we did. And before going into the curved configuration, I will just briefly mention the recent results on the observational constraints that the Planck collaboration, DESI collaboration, and EBOS collaboration did on the one parameter extension of standard model of cosmology, so that without making really fast assumptions on the curvature. So we should just be briefly reminded about the observational constraints on the curvature that we use on the standard model. And then afterwards, I will talk about our results on the curved ODD symmetric configuration and give our results on that. So let's start with our motivation about why we work on the alternative theories of gravity, because within the framework of general relativity, the theories that we use do not match with the observed amount of matter, such that we need to include some unknown sources of dark energy and dark matter components into our models to match the observed amount of matter. So so that we can match the observations. And as a result, the low energy limits of string theories provide a very good alternative set of gravitational theories, both for explaining the early universe evolution and the present large-scale structure of the universe. And the model of ODD symmetric system, both coming from a symmetry dictated model, and it's well motivated from the supergravity cosmology. It's very intriguing to work on and compare it with the phenomenological stringy model of chameleon cosmology. That's why we wanted to first make our analysis on the flat ODD symmetric system, and then compare it a phenomenological model where a matter and dilaton coupling is present, and compare its linear phase dynamics in terms of the dynamical system analysis. So another good advantage of ODD symmetric system or another advantage of ODD symmetric system is that when you stabilize the dilaton, where in the stabilization of dilaton you recover the standard Friedmann equations for radiation in the string theory, but when you stabilize the dilaton, you recover the standard Friedmann equations for any matter source rather than just radiation. So that's why we wanted to work on in both comparing with the phenomenological models and being a symmetry dictated, well-motivated model. That's why we wanted to work specifically on the ODD Friedmann equations. So the reason that we analyze these models using a linear system stability analysis in the framework of dynamical system analysis is that it's very elegant method that provides insights to cosmological models really elegantly, because let's give an example on that matter. If you think about a universe configuration where there is matter, radiation, and let's say cosmological constant, it is very easy to see the evolution of trajectories that is starting from the radiation domination and going into the matter radiation equality and then reaching to the cosmological constant domination. It is really easy to see that in the phase space trajectories. That's why we choose to use linear stability analysis in these models as well. And also, you can make comparison of models by their both number of critical points and their behavior in their phase space by just calculating their autonomous system, like constructing their autonomous system and finding their critical points in the phase space. By the way, you can interrupt me at any point to ask questions, so I will gladly try to answer them. So let's give a brief overview on the method that we use and see how the algorithm works. First, we take the Friedmann equations of the model and define the model meaningful phase space where dynamical variables from them. And then we construct the autonomous equation system. What is an autonomous equation system? It is a system that the evolution of the defined dynamical variables does not depend explicitly on the independent variables of that dynamical variables. Meaning that if you have a set of phase space variables, let's call it x of t, where the evolution of x of t does not depend explicitly on x. It will be a function of x of t. So this parts will be more meaningful when we move on to the examples that or the results. And then after creating the autonomous equation system, we go on about finding the critical points of that system. And then since we are doing a linear stability analysis, we need the Jacobian matrix of the autonomous equation system. And we evaluate the critical point, evaluate the Jacobian matrix on those at those critical points, so that when we calculate the eigenvalues of the Jacobian matrix, we understand the behavior of that critical point in the phase space, whether it is an attractor point, it is a saddle point, or it's a source point, or it can be a stable spiral as well. So the cosmological setup we take at the first step was take the ODD complete Friedmann equation from the work of Angus et al. Here we see that the flux contribution and energy density and the dilaton. As a first step, what we did was to fix the time-lapse function to 1, and the equations simplified a little bit more. And we are trying to simplify as much as possible to get the equations in a form that we can turn into the autonomous equation system, because as the model gets complicated, constructing an autonomous form gets a little bit harder. So we set the lapse function to 1. And since we are expecting the universe to be especially flat, as a first approach, we set the curvature as 0. So when you set the curvature as 0, you see that the equation simplifies a little bit more, and we can do linear stability analysis. And then to complete the set of equations you see here, we need the continuity equation as well. And we take our equation of state parameter as constant, such that we can solve the continuity equation, and it gives this form, where the first part is the usual, the rho 0 a to the minus 3 1 plus omega, which we know already. And then this part comes from the fact that when you couple dilaton to matter, this is the contribution coming from that part. And lambda describes the coupling of dilaton to matter, and we take omega as the perfect fluid's equation of state, which is the pressure divided by the energy density. And now we start our algorithm of linear stability analysis, and we construct the autonomous equation system. To do that, we need to do a bit tidying on the Friedmann equation, such that on the right-hand side, we left only the unity and everything else on the left-hand side. So we see that we need to define our phase space variables as meaningful as possible to the evolution of the universe of that model, so that we can understand how each component contributes to the evolution. In order to do that, we take the kinetic energy part as x and flux contribution as y, and take the energy density part as omega. And by rewriting the Friedmann equation, we arrived here. You see the constraint equation, which defines the geometry of the phase space. In this case, it gives a hyperboloid of two sheets phase space, which already shows an interesting feature, because it's not very common to find a phase space geometry like this in usual cosmological models. So it's already intriguing to work on this model and continue to work on this model. So we continue finding the evolution of these parameters by just taking their derivatives with respect to the logarithm of the scale factors, let's say. So first we take the time derivative of the parameters and then divide it by h. So it gives like dx over dn. So we arrived these equations, autonomous equations. And by meaning autonomous equations, you see that the evolution does not depend on the time parameter explicitly. Here you see the x double dot over h square and h dot over h square, but we also write those expressions in terms of the dynamical parameters. So this is the meaning of an autonomous equation. The evolution depends on the dynamical variables itself explicitly, not the independent variable. So we solve this system to find the critical points. But before going into detail about the critical points of a flat ODD complete universe, first we should ask ourselves, what is meaningful result when you do a linear system analysis, linear stability analysis on a cosmological model? What we want to see in a phase space in terms of the behavior of critical points. So in an ideal analysis, we need a source node, like in the example of radiation, matter, and cosmological constant. We need a source that the trajectory starts evolving, which is also called the pastime attractor. We need a saddle node, which in terms of our example corresponds to the matter domination, where the trajectories pass by to that node. And finally, we also need at least an attractor node as a late time attractor. So if we have all these three behavior critical points in our system, it is plausible to continue work on in the linear stability analysis framework. So you see in the flat ODD complete Friedmann equations all have these 3 points. So as a result, we find like 3 and 4, there's a total 7 critical points, which some of them attractors, some of them saddle, and we give their location on the phase space, as well as their eigenvalues and their existence conditions. And whether they are changing with the equation of whether their behavior changes with the equation of system parameters. So, but it's a bit hard to understand the overall picture from this table. So we do what we call like the plotting the equation of system space dependence on these critical points of behavior. So as you can see, the point A's behavior doesn't depend on the lambda parameter. When yeah.
So I mean this is after you linearize the Friedmann equation, you have.
So sorry, I didn't quite understand the question.
I'm not familiar with all this step, but have you linearized the Friedmann equation first? You have some linearization of the Friedmann equation.
The Friedmann, the linearizing the Friedmann, no, we didn't linearize the Friedmann equation. The linearization part comes from the fact that when you construct the autonomous system, you calculate the Jacobian, because the linear contribution comes from the first derivative. So the linearization part comes from the fact that we use Jacobian and its eigenvalue evaluated at the critical points. That's why we call it linear stability analysis.
I have another question.
Yes, please.
You fix the equation of state from the very beginning. The equation of state is a fixed parameter.
No, we didn't fix the equation of state. We just said we take it as a constant. It doesn't evolve, so that we can solve the continuity.
Yeah. So in other words, it doesn't change during the evolution. The equation of state does not change, but you expect it to change during the evolution of the universe. I mean, the equation should change, right? For instance, now we have equation. Now we have the cosmological constant. In the past, there was radiation. Before, I don't know. So,
the effective equation
to change.
The effective equation of state evolves, yes, but the equation of state that I'm talking about here is about this energy density's equation of state. Effective equation of state evolves, yes. Sorry?
So in other words, what do you define by equation of state? It's not. So it's not clear to me what is your definition of the equation of state.
Equation of state is the perfect fluids equation of state here, omega, which I defined it as the pressure divided by the energy density.
But the pressure of what? The total pressure of the universe, or just the one of the method?
Just that one component that I take as it is either as a radiation, matter, or scalar field pressure, not as a whole. I'm not talking about the effective equation of state here. That omega is just the equation of state of the component that I will give in the upcoming slides. Like whether if I take it as a radiation, then I will give omega as a 1/3 value.
Then if you show the table, for instance, with some attractors or some critical points, you had a table with critical points. Each of these critical points correspond to what kind of evolution of the universe. So
I didn't understand. The equation of state here is the component that we give. It's belonging to the component that we give to the model, not as a whole.
Yeah, I understand. No, my question is, what is the whole equation of states? In other words, the universe if the universe reaches one of those critical points, what is its evolution? What is its
oh yes, I will come to that part in let's skip it. Let's skip a bit further. Then that when we take set the equation of state to radiation, let's say, I will come to this part in a bit later. But here, let me just to answer your question. Here you see the black dashed line. This is the equation of state of the whole system. This is the effective equation state. Yes, it evolves as the universe changes and reaches the attractor points. Yes. So was that your
Please
question?
go ahead. Sorry.
Okay. So in terms of the equation of state parameters omega and lambda, we see that the points change characteristics. Here you see the red shaded areas are the attractor nodes, greens are the source nodes, blues are the saddle nodes, and grays are the stable spirals, which is called the focus points. And the dashed regions here you see are the regions that is not allowed to take, because they either make the eigenvalues of the Jacobian matrix infinite, or they make the dynamical system parameters infinite, or they make the dynamical system parameters complex, which we do not want. So let's move on. So this is the result on the flat ODD universe. So as the question was whether the effective equation of state was evolving, yes, of course it's evolving, and it is very interesting to see its evolution in the ODD complete universe when we take the flat, because you see on all these components, the black dashed line is the effective equation of state. It reaches to by the way, the purple horizontal lines describes the 1/3 and -1/3 values. So even though we take the flat, we started with the flat assumption, the effective equation state reaches the -1/3, which is of a curvature. So that might be the first indication that whether this stringy gravity ODD complete system has a preference to non-flat cosmologies. So another point that I would like to make is that the attractor point in all these cases at 0, 0, where x is 0 and omega is 0, which corresponds to the flux domination. And in the radiation case, it doesn't have an acceleration at the attractor point, but in the scalar field and dust case, we see an acceleration, which is on the right-hand side of the figure. It is a red dashed line, which we plotted the deceleration parameter, where it's lower than 0, the universe accelerates.
Hi, excuse me. Sorry, can I ask a quick question? Can you hear me?
Yeah, yes, please.
Yeah, so I'm wondering, with scalar fields, are you considering an arbitrary potential, or are you just considering a massless scalar field?
Oh, there is no potential for the scalar field here. No potential.
So potential is 0 here. So it's like, is there equals 1 solution? Like, I mean, the equation of state equals 1.
No, sorry.
Is there the solution with the solution with pressure equals energy density? Is that the so it's the particular value we're looking at?
I'm sorry, I'm having a bit hard time to understand your question. Can you please repeat that?
Yeah, just asking, are you considering a scalar field with a general potential, or the potential equals 0?
The potential is not we don't take account of the potential here. There is no potential for the scalar field here, just the kinetic term.
Okay, so it's like a modulus, or like, fine. Thank you.
You're welcome. So let's see the results on the chameleon cosmology that we did. So the first reason that the motivation that the comparison of chameleon cosmology with the ODD complete system is that in the chameleon cosmology there is the arbitrary function f that is coupled to the matter sector. So we again find the equation of equations of motion of the system and Friedmann equations, where we rearrange the Friedmann equation to find the critical points and define the phase space variables. And again, to construct the autonomous system and compare it with the ODD system, we define the phase space variables of the chameleon cosmology as similar as possible to the one of ODD complete system. So again, here X defines the kinetic energy, and Y here, instead of a flux, this time it's a potential contribution, and omega defines the energy density. So we take the coupling function as a positive, and omega also as positive, therefore. So this defined dynamical variables is when you plug the defined variables and rewrite the Friedmann equation, we arrived at the following constraint equation, which has much simpler geometry, and we find the autonomous equation system again previously. But here now, before analyzing the system, we need to pick a form for the potential and the coupling functions f. So we in this work we choose to choose an exponential form for both potential energy and the coupling function, which we will set the parameters a and b later on to understand the to match the contribution coming to match the contributions both coming from the ODD and the chameleon cosmology. So here on the left-hand side, we define the chameleon cosmology linear stability analysis dynamical variables, and on the right-hand side, we had previously defined ODD, the phase space variables from the ODD complete system. So to match the first contribution of the omega here, sorry, if you look at the defined omega parameter on the ODD system, the exponential factor comes with, if you square this term, you get a 2 phi. To match this contribution in the chameleon setting, we set b to 2, but we need to be more careful with the potential because we don't want to break the ODD symmetry. So we take the potential as a trivial potential. So we set a to 0 to have a constant scalar potential to preserve ODD symmetry. And also compare with the flux contribution on the ODD system as well. So here is the result of the chameleon linear stability analysis. The system has a total of 3 critical points, which doesn't depend on the equation of state parameters. A acts as a source, B acts as a saddle, and C as an attractor. And the accelerating regions are shaded with blue again here. The attractor point corresponds to the domination of the potential energy, as you can see on the right-hand side figure, and the acceleration starts when the potential comes into domination. But here we see that the effective equation of state in all those 3 cases relaxes to -1 value, which is of the dark energy. So this is the difference between the chameleon and the ODD complete systems linear stability analysis, where we found a -1/3 effective equation of state around the attractor point. Here in the chameleon cosmology, we find an effective equation of state of -1. And the acceleration always occurs during the scalar field's potential domination. So let's summarize both models' linear stability analysis. So as expected, the ODD extended system has richer dynamics than the chameleon one, as expected, because even the phase space geometry shows us that the chameleon one has an elliptical one, but the ODD complete system has a hyperboloid of 2 sheets. But the hyperboloid of 2 sheets phase space can be turned into a form of a sphere with making changes in the dynamical variables to compare with other phenomenological models in the context of linear stability analysis of cosmological models, and see whether they are similar to other phenomenological models in terms of their critical points of behavior in their phase spaces. So although the phase space structure of both systems differ, we see that the quantity and the behavior of critical points are the same in terms of whether in terms of number of critical points that we look in the phase space that we find. and their behaviors are the same. And also the evolution of the universe in both cases show that the dominating factor around the dominating factor of flux and scalar potential during the acceleration phase, and their attractor points corresponds to the flux in the ODD setting and scalar potential in the chameleon setting. So our intuition was at the beginning was proved as correct because we were expecting a similar behavior between the phenomenological model chameleon because of the coupling with the dilaton, and the ODD setting, the general coupling of dilaton to everything else. But the difference, yes, please.
So ODD cosmology is written in string frame, Jordan frame, while chameleon is written in Einstein frame. I mean, this frame difference, does it matter in your conclusion, or does it?
It's an excellent question. We didn't check whether the results depend on the chosen frame. We did our analysis on the Jordan frame. We didn't do any conformal transformations on the equations, but it might be interesting to work on that as well. Yes, maybe there is a different behavior in the Einstein frame. There might be a different behavior. Yes.
Stability itself should not depend on the choice of the frame. Stability. It's just
was your question the stability depends on the choice of the space variables?
No, the frame.
I don't know in this setting. I don't know in general, because we always work on the. I remember, if I remember correctly, we always try to work on the Jordan frame, but maybe we should do a analysis first on the Jordan frame and then change the frame to Einstein frame and compare their face-to-face dynamics. Yes, then we should be able to understand whether there's a dependence on the chosen frame of either whether Einstein or Jordan. But we didn't do that here. So the striking difference in the comparison of ODD setting with the chameleon setting is that as we see, the effective equation of state relaxes to -1/3, which is very interesting because we assumed a flat universe at the beginning. Sorry. So before going, yeah.
Clarify better, because I don't understand the point. So the fact that the universe is flat, it can have any equation of states. I mean, it can have. So why you say that there is a curvature effect?
I'm not saying there's a curvature. I'm just saying that the resulting effective equation of state is that of a curvature. I mean, because
this equation of state is quite peculiar because it's the boundary between acceleration and non-acceleration in standard cosmology. I don't know in this setting, but in standard cosmology, -1/3 is the boundary between accelerating and decelerating universe.
Sorry, I didn't quite understand the question. Apologies. Can you please repeat that?
So if you just take the Friedmann equations and
yes,
you add the deceleration parameter Q minus A dot A divided by A dot A dot A divided by A dot. The deceleration parameter. The deceleration parameter changes sign when W is either larger than -1/3 or lower than -1/3. You are an accelerating expansion when W is less than -1/3. So it's a peculiar value. So this is the universe in standard cosmology, when W is equal to -1/3, the universe is neither accelerating nor decelerating. The deceleration parameter is 0. Right?
So you're saying that the effective equation of status signature is decides the acceleration.
Yeah. This is the standard cosmology. The deceleration parameter Q is equal to 0 when W is equal to minus 1/3. So this is a quite peculiar value. I'm just commenting. It's just a comment.
Oh,
But it's
okay.
in standard cosmology.
I don't know here. Yes, exactly. I don't know if.
Oh, yes. I understand now. I understand. In Starling cosmology, when the it's Q is 0 when you're saying that, right?
So what about
Okay.
here?
Yeah, the interesting point is here is that because we see an acceleration when effective equation of state reaches -1/3.
I see.
Because this is interesting result. That's why it's very particularly interesting. Because this is very different than the standard cosmology, and we see that the interesting properties of the stringy gravity of ODD complete setting in the when we do a curved analysis as well, which I will come to that later. Because we
minus 1/3 is not special in this setup. It is quite interesting that you get. So it cannot be a coincidence why we get exactly minus 1/3.
Yeah. I mean,
Because-
I mean, it looks a bit coincidental, but when we do an analysis on the curved or the complete cosmology, we see that similar results as well. Let's give a sneak peek. Let's see. So before again first doing the analysis on the curved or the complete Friedmann equation, let's look at the current recent observational results, which given by the early universe with the Planck collaboration, which prefers the one parameter extension of lambda CDM model, prefers the flat universe, as well as the BAO coming from that DESI collaboration and EBOS collaboration did, which combined with the temperature and polarization of CMB and the BAO and Pantheon data, and all together, they always shows a flat universe preference on the special curvature of the universe. So it is that's why it's very interesting to see, even though in the flat case we see a -1/3 equation of state, because we already assumed the flat special universe. But let's see the result on the linear stability analysis of non-flat geometrical ODD complete universe. Again, we just started with the same equation of dynamical equations, and we just lifted the flat assumption on the curvature, and then we defined the omega k parameter as shown here. And now our constraint equation again just have the omega k value, and we find the evolution of those dynamical parameters. So here, out of 9 critical points on the non-flat ODD complete system, we see 3 of which shows a non-zero curvature than omega k. So for C1 point, we see it's always exists, doesn't depend on equation of state parameters, and shows a saddle point behavior. So that means that at some point of the evolution of trajectories, the trajectories will arrive at that C1 point, critical point, and then move on to the evolution. It's not an attractor point. But on the C6 and 7 exists for only when the equation of state is less than or equal to -1/3. And the condition on the lambda is that it shouldn't be equal to 2. So the curvature of those 6, 7, and 7 points depends on the equation of state parameters. So in order to see that clearly, again, we chose to plot the behavior of those points based on the omega and lambda. On top, you see the gray shaded areas is the not allowed region, the forbidden region, that we can't take those omega and lambda values. And purple shows an open universe contribution, and the cyan region is the closed universe. So we don't see any flat contribution on the 6 and 7 points, critical points. So on the bottom, you see again the shaded region here is forbidden. Red is an attractor, and gray is a spiral, and here blue shows a saddle contribution. So the dots represents the accelerating regions. So the allowed values of equation of state parameters in the points 6 and 7 always accelerates. But you see in the open universe part, the behavior of the point is an attractor one. Even then it's a stable spiral, it's an attractor point. So when you take the equation of state parameters in the allowed region for a closed for an open universe, there is in the phase dynamics of the system, there are points that's attracting and accelerating on the open universe configuration. So comparing this result with our result with the work of Lee et al., we see on there they did a Monte Carlo analysis on the late time cosmology with Pantheon and that data and the absorption spectra of quasars. And the 6-parameter Bayesian analysis shows that incredibly dominated curvature contribution with 0.9. But the interesting point here is that the Pantheon data, you can explain it with you can explain the result observations with the omega when n is 0 and curvature can be an open one. Also, you can find for parameters such that the curvature can be give results of a closed universe. So by just looking at the Pantheon data, I'm not sure about we can just really get excited, but it's a really interesting result as well. So we as a future work we might or we should do a similar analysis using early probes of the universe such as the Planck combined with the BAO data and the Pantheon data. But as you can see here, the stringy gravity of ODD complete Friedmann equations shows signs of preference on the open universe configuration, both in the dynamical system analysis approach, both and the observational constraints. So let me just summarize everything we did. So we can compare the phenomenological string cosmological models with the well-motivated models coming from modified supergravity ODD complete cosmology using linear stability analysis along with the additional constraints coming from the observations. And we see that the curvature expanded lambda CDM prefers a flat universe, very contrasting to the string cosmology. And the string cosmology of ODD complete universe has a specific preference mostly on the open universe. And when we look at the open universe's configuration, the accelerating critical points of the ODD setting shows the attractor or focus behavior, whereas a small subset of omega and lambda values allow for a closed universe, but they are not an attractor point. They are only a saddle node characteristics. So it might be a sign that even though there is not an attractor point in the ODD setting of an open universe that is accelerating, we can have a point where in the evolution of the universe there was a period of preference on the curvature, even though we see a flat universe now. So that might be that saddle points is understanding. So as I said before, we need to make further analysis to understand the behavior and the preference of the curvature in string cosmology by making a Bayesian analysis, Monte Carlo analysis on the ODD complete cosmology with the BAO data combined with the Planck Pantheon. And we can do another work which we can compare the scalarization or the screening mechanisms of dilaton matter coupling in the models with a certain symmetry dictated motivated models, which can lead to observable effects on the structure of compact objects like neutron stars. So by that, I think I'm done. Thank you all for your attention. And if you have any further questions, I would like to answer them now.
Questions? Let's thank God. So I have a question.
Yes.
So yeah, thank you very much for your nice talk.
Thank you for your invitation.
So you said about this BAO data and I mean within standard lambda CDN, BAO data constrain the flatness of universe. Yeah, universe should be flat. But if you change it to ODD cosmology, do you think one can avoid that constraint because the underlying theory is different? Or what is your perspective?
I expect that if we not just BAO data, but if we constrain it with the early universe probes like Planck data, we should see we should see a change in the preference of curvature, because we expect it to be flat, but I'm not sure about the string of gravity constraints. But we should do another analysis with Planck data combined with the BAO, which is like a late universe probes, along with Pantheon as well. But my expectancy is that the CMB data will constrain the curvature. Yes, please.
Yeah. So yeah, sorry about the audio, but yeah. Just to check my understanding. So are you mostly working with the constant equation state, like constant, like you're looking at a perfect fluid, for example, with constant omega, constant lambda, and then so how do you how do you then extract the effective like W effective or something in that?
I'm so sorry, I am having a bit trouble to understand your question. How do I extract omega?
Yeah, so I think in this you jump from having like constant small omega, like say 1/3 for radiation.
Okay.
So, and then going to an effective equation of state.
Oh, wow.
So sorry.
Yeah, the mic is not picking up your question, I believe, because I am having a bit trouble understanding.
Maybe you could try writing it in the chat.
More
Yes,
questions? Pro line? I got one small question.
Yes, please.
So could you give me a comment for the possibility for closed universe in ODD cosmology? Was it just a saddle point?
Are you talking about this point?
Closed universe, yes.
Yeah.
Oh, the closed universe one. Yes, there's a small possibility of a closed universe where the C6 and C7 points have, but I mean, it corresponds to, let's say, like -1/2 equation of state for the omega and really large numbers of dilaton and matter coupling, like 1.7 or something. And it always shows a saddle point contribution, but I mean, it's still a possibility. Oh, and also it is a possibility of a closed universe, but it is a saddle point. So there might be a period of time where in the evolution of a string of gravity evolution, there might be the dependence on the curvature closed universe contribution coming from the C6 and C7 points, but it's not always there because it's a really small subset of equation of state parameters. I think the question came from Professor Angus from the chat. You started. Oh, okay. No. Here we just only consider only one component contribution, but we can always add another contribution, scalar plus radiation. Yes, we can do that, but in this work we only considered only one contribution. But this will make the phase space dimension larger because we need to add another parameter to the phase space. So we need to consider. We need to do another analysis on that, but I can't really say here without doing the calculations. Scalar fleet plus radiation would result in an attracted points. I can't really just comment on that without making the analysis myself. But it is possible.
What is your definition of effective W, equation of state parameter?
Oh, I just define it as when I rewrite the Friedmann equation in the form of 3h squared equals 8 pi g and a rho. That I combine everything else to the effective energy density, and then calculate the equation of state from there, which I think it was corresponding to -1 minus 2 divided by 3h dot over h squared. So that's how I define the effective equation of state.
So Stevens, another question from chat.
Oh, okay. Sorry. Okay, awesome. Yes, no. We didn't consider it, but an scalar field with an arbitrary potential is an interesting study. I will really, I think I will consider that work as well in the future. Yes, and matter with a varying equation of state is also another interesting point, which I would like to see the effect on the cosmological dynamics. Yes, thank you for your question. These are really interesting. Yes.
Yeah, thank you very much.
Thank
Yeah,
you.
thank you for the interesting talk.
Thank you very much.
I have a very simple question. You made some simplifications. You at the very beginning of studying, you tried to simplify the equations.
Yes.
You are then comparing with the numerical analysis of real time. So the two models are the same or not?
Oh, the two models are not the same, but they have similar characteristics in the application of dynamical system analysis. They're not the same because we see that the phase space differs immensely because the ODD complete universe has a hyperbolic of two sheets, which is highly unusual to see. But in the Chameleon cosmology, we have all.
Just an approximation.
Yes. It is an indicator that it's a starting point of comparing the phenomenological models with the well-motivated string theory models. It is not a direct equality.
Suppose that you didn't do any simplification. The equation would still be autonomous.
But the simplification we did on the Friedmann equation was just fix the time component gauge function, lapse function, which we set to n equals 1. There is no another simplification to the equations. They are just as it is.
In other words, you could actually do an analysis of the critical points of the autonomous equations also with a full model. It's only a question that the phase space is very complicated. Is this the point?
Sorry, I didn't quite hear the question. Apologies. Can you please repeat that?
No, I'm just saying that if you consider the full model without simplifications, the equations are still autonomous, right? or no?
In the autonomous equation system, we didn't do any simplification. We just take the,
No, one step earlier.
okay, here.
When you take the
Here.
full model and then you want to get some autonomous equation. In order to get, so the simplifications that you did were required to make the equations autonomous, or the equations would be autonomous also in the full case?
No, I don't know if the I mean, this, to my knowledge, this is the full case. The only simplification that we did was set the lapse function to 1.
I see.
But I mean, in the full perspective of this part, yes, you can create. I mean, it's just defining another set of dynamical variables, which you can again find an autonomous form. But I'm not saying that you can apply this method to any cosmological model, because you might write a model that you can't put in a form in an autonomous form, because
Exactly, this is my question. So
yes, you can't do linear stability analysis, or you can't put the Friedmann equations in a form, or define phase space variables and put in a form an autonomous equation system. You can't do in any system.
Yeah, of course, this is the point.
Yeah.
So in principle, the full model is not autonomous. You would have some explicit dependence on time or whatever, you would have, the equations would not be autonomous, and so you cannot do an analysis of the critical points.
Exactly. You try to create the autonomous equation system, but there will be some in some models there will be some terms that is always dependent on the independent variable. So you see, like, maybe there is a phi dot here, but you can't rewrite that term in terms of the defined variables. So you can't close the system. So that then you can't do the linear stability analysis. Yes.
Okay.
So there was a question coming from the chat,
Yes.
I guess. Yes.
One more questions from Wayne Park.
The question is, does the closed universe region agrees with saddle region exactly, even beyond what you have shown? I guess the question is for this part. Let me just go over there really quickly. Yes, here, right? Yes, these two plots match exactly one another. We didn't do anything else. We just first plot the dependence of curvature to see whether it's open or closed, and then we do the same thing on the same equations, but by just looking at the whether the eigenvalues are the positive, negative, and so on. These two plots match 1-to-1 exactly. So that was your question, I guess. Beyond that, we don't. I mean, beyond that, what you mean beyond that is if we take the omega as -2 and lambda as 3 or something. We didn't check that part. But in the sense of this regions, they match exactly one another. So oh, you're welcome.
Yes, I have another question.
Yes,
So,
please.
I mean, you mentioned in your later part our paper, the comparison with the real data. Yeah. So one
Yes.
result over this paper is that without explicit method, raw pressure and T0, the vacuum geometry itself fits with the data very well without and do
Yes.
you, from your stability analysis, can you comment on that vacuum geometry?
Oh yeah. Yes. When you look at the Pantheon data, the absolute distance modulus, you can fit the data, but you can also fit the Pantheon data with zero matter and 0.3 cosmological constant, which corresponds to an open universe. And also you can do a similar fit with let's say 0.45 matter and this is 0.9 cosmological constant, which corresponds to a closed universe. But that's why as a further study, we should make the Bayesian analysis with also the early universe probes such as Planck, combined with the Pantheon supernova data.
No, my question is about your stability analysis.
Yes, yes.
Have you done stability analysis on vacuum? Is that, can you comment on that?
The vacuum? No. You mean by not taking any energy density or flux and just by curvature, right?
Yes.
No, we didn't consider just by taking a curvature and writing the equation in that terms. Yes, but if we have just the curvature without anything else, I'm not sure what will be the result of the stability analysis. Maybe we should check that further.
I guess, sorry, I guess the question is like, if you just have the dilaton and H flux and curvature, say.
Oh yeah. We didn't check that. Yes, but it will be interesting to see what will be the result of that model as well. Just the flux and the curvature. Yes, it will be interesting. Which if then the result will be the same, then maybe it should be a indicator again as well, the dependence on the curvature. Yeah. If there will be a just flux and the curvature, it will be an interesting result. Yes.
I mean, I tend to think that vacuum geometry is an alternative to the zeta.
Yeah.
It's expanding universe, but not precisely this universe. So it would be interesting. I mean, worthwhile to study that property of that vacuum geometry further.
So sorry, can you please repeat the
As
question?
an alternative to the zeta, the zeta is the standard first approximation in the standard cosmology.
Yes.
But in ODD cosmology, that vacuum geometry is the first approximation to real universe.
Again, sorry. Apologies. I'm really having trouble to understand the question. The sitter? What?
So I mean, the zeta is the first the good approximation to real universe in the standard cosmology.
Okay.
But in ODD cosmology, the vacuum geometry, which has only dilaton and H block, is probably the alternative to the zeta.
Okay.
So it should
Okay.
be it should be worthwhile to study the vacuum geometry further. And I just want to know whether your analysis include vacuum already in your plot.
Oh, I understand now. No, yes. It will be, yes, it will be interesting because yeah, in the string gravity, it might be the vacuum geometry and the curvature dependence will be the dominating and the preference, yes, as opposed to the sitter in the standard model. Yes, if I understand correctly. Yeah,
Yeah.
but it should be studied further again. Yes, because the results are interesting.